Okay, this video will be about statistical interpretations in SPSS and any other statistical software or software for data analysis. So I'll be explaining. I'm sure people have seen something like stars, what they mean, what are p-values, and how to interpret everything. So the stars are called these show statistical significance. They show that values are statistically significant. The formal term is asterisk. They are called asterisk or confidence intervals. They show the values, the coefficients are statistically significant, usually betas. So the 3 stars. Okay, let me just start at the bottom. When you don't have a star, for any value which has got a p-value greater than 0.5, 0.5 can be in percentage form. So any value greater than 5%, if you convert it with a calculator, is not statistically significant. Anything greater than 5% or 0.4, any p-value. So p-value or sig values are just the same. They just show statistical significance. Then we'll just skip this one here. Any p-value less than 5% is significant at 5%. So if it's p-value less than 5%, it's significant at 5%. So the catch is it has to be less than 5% but greater than 1% for it to be significant at 5%. If it's less than 1%, it's significant at 1%, but if it's greater than 0.1%, it's that means it's significant at 1% or 0.1. That means it has 2 stars. 3 stars is any value less than 0.001, any p-value. That means it's significant at 0.1%. Let me show it properly here. I think this one will do more justice. So this is what I mean. In fact, we're supposed to add something here. Insignificant if got a beta value, beta coefficient, if p is greater than 0.005. So we start with the insignificant part, which is basically p is greater than 5%. So if p is greater than 5%, the p-values allow you to determine if the coefficients are statistically significant. So we just start properly from here. If the p-value is greater than that, that means the coefficients or the beta values are statistically insignificant. Once you have a p-value less than 0.5, it can be significant at 5%, 1%, or 0.01%. Now the difference is that if it's significant at 5%, it has to be greater than 1% but less than 5%. So for it to be significant at 5%, or you can use the decimals. The decimals are much better. So these in the brackets are what we call inequalities. These I've just put in bold. They are called inequalities. You can also represent them with the actual p-values. I think that's the best way of representing. It shows more scholarly transparency. If you show the actual p-values, I'll talk about that near the end of the video. So for it to be significant at 5%, it has to be less than 5% but greater than 1%. For it to be significant at 1%, it has to be less than 1% but greater than 0.1%. For it to be significant at 0.1%, it has to be less than 0.1% as it approaches 0. So this is sometimes in the softwares it's shown by this 0.000. If you see this, or maybe there's just point in the softwares, let me just perform correlation analysis and regression, just to show how that looks like. So we go on analyze, correlate, bivariate. Okay. So what can I put for control? Gender, age. Okay, entrepreneurship, education. Okay, let me just put school type. So we take the means and standard deviation, exclude cases pairwise, not listwise. We also highlight Spearman correlation. I'll talk about correlation in the other videos properly in a video dedicated for correlation. I'll press OK. So basically, I forgot to put the x variables, pardon me. So we go to correlate, bivariate, then these are the x variables here. So cognitive, structure, relational, and it's prudent for you when you're making a correlation matrix, you arrange them in the size of magnitude of the betas. Okay. So this is the non-parametric version of correlation, Spearman correlation, and there's the parametric Pearson correlation. So these are stars here. For correlation analysis, the software generates stars. This is SPSS version 23. So it generates stars, asterisk, sorry. So these are asterisk, showing that this is statistically significant, the relationship. So this is a bivariate correlation matrix. It compares two variables at a go. So here we compare entrepreneurship in agriculture against entrepreneurship in agriculture, gender against entrepreneurship in agriculture, age against entrepreneurship in agriculture. So you place the y variable at the top there, then you interpret with the first row. So I'll properly explain what everything in a video dedicated for correlation analysis. So these are the betas. So this means that this is statistically significant at this is significant. It's a two-tailed test. That's why these are two-tailed tests. Statistically significant at 1% here. So if we go back to this, so it's significant in this bracket here. In this bracket, so it's significant. In this bracket here, it's very significant. So that's about interpreting p-values. So this one is significant at 5%. Now let's do hierarchical regression analysis, or any maybe even simple regression. So we go analyze, regression linear. So the independent variable is entrepreneurship in agriculture. So for linear regression, we can just do both hierarchical and linear. So we put gender, age, our control or covariates. Which other one did I pick? Education, type of school. Okay, so this is what we call, this is linear regression, simple multiple linear regression. I'll do both hierarchical so that you see the difference in tables. So if I remember, cognitive was the smallest, but structural, relational, social capital, entrepreneurship skills, perceived behavior control, attitude, subjective norms. Okay, so now these are the settings for linear. You tick that, you tick collinearity diagnostics, you tick yes. Okay, plots, zip red goes to x, that goes to y. Okay, some settings produce unnecessary data, yeah, so we untick that. Options, exclude cases pairwise. Listwise removes variables with missing values. Pairwise, at least you test the entire data set. Okay, I think we're good to go. This is for simple linear regression. Now for statistical interpretation, we go to the coefficients table. Coefficients table. Coefficients table. Yeah, so you use this to know if something is statistically significant. So you multiply this by 100. So these values here, they are statistically significant here by the sig value. So you go to they are what we call standardized beta coefficients. Then they are unstandardized beta coefficients and standardized. We use the standardized because they are more of standard. How can I best put it? They make comparison easier. That's how I can best put it. Yeah, so this is significant at 0.1%, so you can add 3 stars here when you're making the table. So 3 stars, 3 stars. So we use the standardized beta coefficients here. Yeah, then this is what we call the variance inflation factor. I'll also talk about that later on. Okay, sorry for that. Let me queue. Okay, so this is for simple linear regression, multiple linear regression. I'll explain the difference in the video. Then for hierarchical, you can perform hierarchical as well. Okay, analyze regression. So we just remove all the x variables here. Press shift, scroll down, they are out, so we're left with covariates only. So we press next, the settings remain the same. Then we add a variable, cognitive social capital, structure social capital, we add in relational social capital. You add them in order, ascending order of their magnitude. So Entrepreneurial skills, you add. Perceived behavioral control, you add. Attitude towards entrepreneurship, you add. Subjective norms, this is now hierarchical. Okay, this version of SPSS has got 9 blocks, so that means it can handle up to 8 variables in terms of hierarchical regression analysis. So I can then tell which results will pass hypothesis testing by the sig values. So these are sig values here. It's also called p-values. They are p-values. So you go to the last model here. This is significant at 0.1%. So these are the beta. So this beta is significant. So this one has passed hypothesis testing. This one has also passed hypothesis testing. This one has a passed hypothesis because they are significant, since this is the last model. So basically these sig values help us interpret if a beta value is statistically significant or not. So in fact, these were I think I was mixing up. These were the beta values here. I don't know if I was mixing up. This one, that one. So these help you to know which beta value or beta coefficient is statistically significant. So that's mainly the range of significance. So from 1 star means, or 1 asterisk means that it's significant at 5%, 2 at 1%, 3 at 0.1%. Now the best way of reporting this, for example here, our beta here is 2.82. The best way you can report it like this. Okay, let me pause the video a bit. Okay, so that beta here is significant at 0.1%. So you can just that's 0.2. Where is the beta again? That's 0.282, which is significant at 0.1% or 3 stars. So here you can assign 3 stars, but when reporting it in a paragraph, you can opt for inequalities like this. So this is the beta. This is how you show it in maybe a paragraph. Or the best way of showing it is using the actual p-value. The actual p-value there is 0.000. This is the most transparent and scholarly way of showing the p-value, using the actual p-value there. So maybe if something is not significant like this one, the actual p-value will be 0.566. So if it was something not significant, the actual p-value would look like 0.566, because this is greater than if you multiply by 100, greater than 5%. This is way greater than 5%. So that's just a way of reporting things. So I think that's it about statistical. So there are other ways of interpreting, but this is the most general way of interpreting some things. Some tests. Most of the tests who follow this order of doing things most of the